Morning, everyone. It's time for the European Quantum Leadership Session 3 on quantum sensing and quantum imaging. So this one is jointly organized by KBN and OpticBB. And before we start, let me introduce you to a very important initiative. So the initiative is the World Quantum Day, which will take place on the next year on the exact date of today. So this initiative want to promote the public understanding of quantum science and quantum technology around the world. And yeah, QBN is very happy to support this initiative and to start the countdown today. And I think we will have a lot of events within this World Quantum Day. It's a very good initiative. So, but back to our session, with which we want to show the world how Europe paved the way to its industrial leadership in quantum technologies. And yeah, many of our data for our digital life come from sensors and imaging devices. You can say they are our sense. And sensing imaging is definitely a hidden champion. So quantum technologies can enable us to go beyond classical limits for sensing and imaging. And today we want to present you some insights into the visions, products, success stories, and collaborations of leading quantum sensing and quantum imaging organizations as keys to position themselves and Europe as a leader. So my name is Johannes Verst, and I'm the founder of KBN and CEO of KBN. I'm also a quantum physicist and innovation and company builder. I founded KBN as an international quantum business network to provide the European quantum community supportive structures and develop a really strong quantum industry in Europe. So we have in Europe a very, very strong quantum community. And with the latest commitments or announcements from the European Commission, from Germany, France, and the Netherlands, we were able to accelerate, or we are able now to accelerate the transformation to a strong industry. So, but public funding and also private funding is not everything. So we also need collaborations, market insights, and partnerships. And yeah, with this aim to promote networking, business creation, and the development of organizations working in the field of quantum technologies and its value chains, QBN was born. And yeah, we do this with a network. And yeah, a network is more than an ecosystem from our point of view, because in an ecosystem, every person and every organization is in charge of their partnerships, of their business developments, of their visibility. And by adding a cluster management that supports all stakeholders and manages the collaboration processes within the ecosystem, provides additional value to all of the stakeholders and to the ecosystem as a whole. So if you want to be part of the European ecosystem and accelerate your business, if you're looking for collaboration partners for fast access to private and public funding, if you are looking for more visibility and talents, okay, my computer has a problem. Yeah, if you are interested in individual tailored support, you are invited to join KBN, and we support you with a colorful bunch of activities and services. We have also scheduled a few KBN meetings as a key element of our network activities. With them, we want to provide a trust-based environment for knowledge exchange and the initiation of new collaborations. And here's a short overview of the upcoming QBN meetings and one QBN webinar. What for you is could be very interesting is the QBN meeting on quantum imaging at the beginning of June, and the QBN meeting on quantum sensing at the beginning of July. And there will also be a QBN webinar with a more high quality content on diamond quantum sensing at the end of June. So you are invited to join us there. So yeah, I want to invite you to create the quantum future together here in Europe. And with this, I want to hand over to Frank Lerch, the Managing Director of OpticBB, who organized the European Quantum Leadership Sessions together with me. So Frank.
Thank you, Johannes. My screen. I have my presentation here as well. So welcome also from my side here from Berlin. In my back, you can see the technology park of Berlin Adlershof, where I'm actually located. Actually also today, so I'm not in home office, but in the office, in the real office today. Optec BB, as you might know from the last presentations, is the regional photonics industry network here in the region of Berlin and Brandenburg. And as you know, a lot of the quantum technologies are based in the photonics technology area. But I'm not going to bore you with the slide that I've been presenting in the last two sessions, the European Quantum Leadership webinars. But I would like to share two information with you this morning. One is that also Berlin, the state of Berlin, the Senate of Berlin is fostering the development of a research cluster on quantum technologies. So there has been a decision in February to spend 25 million euro over the next 5 years on quantum technologies on a research cluster. The details are not clear yet, but Optec BB is trying to play a central role also in developing a network or closer, stronger network here in Berlin. So watch out for some of the issues that we will announce here in Berlin. I'm also very happy that Markus Kudzik is here with us this morning from the Humboldt University and the Ferdinand Braun Institute. So a special welcome and thanks that you are here this morning. And also just one save the date. Johannes has been presenting some of the upcoming dates within the QBN. Optec BB is organizing a rather large, nowadays online symposium and conference. We call it the Photonics Days Berlin-Brandenburg. Last year, for the first time, we had it in a virtual space with some 900 participants from all over the world, basically. It will be again virtual, unfortunately or fortunately, depending on your perspective. The date is set. It will be the 4th until the 7th of October. And I'm mentioning this because we will have again a number of quantum technology sessions. Last year we had actually 3 sessions on quantum technologies. So save the date, mark it in your calendar if you're interested, and I will take the opportunity to announce further details probably in the next session, which will be in June. Yeah, and with that already, I hand over to Johannes. If you're interested in the ecosystem here in, I'm sorry for my telephone, a classical interruption. So if you're interested in the photonics and quantum technology ecosystem here in Berlin, don't hesitate to contact me. I can share my email address in the chat. And now with that, I hand over to Johannes.
Yeah, thank you very much, Frank. Yeah, let me share one more screen slide before we start. So just a few information about the housekeeping. So the European Quantum Leadership sessions are being recorded. You can watch it on demand on the QBN YouTube channel. And if you are in Zoom, you can ask the questions via the Q&A box below. And if you are in the or if you're watching it live on YouTube, you can use the chat window to ask some questions. If you have some general questions, just write us an email. And yeah, if you like the content, you are invited to follow us on LinkedIn and Twitter. And yeah, please also subscribe to our YouTube channel and leave a thumbs up if you like the content. And with this, yeah, I want to hand over to the first speaker. The first speaker is Dr. Frank Setzfand. He is leader of the research group Quantum Optics, and he will tell us more about imaging and spectroscopy with photon pairs. So,
yes,
Frank,
so thank you very much.
The stage is yours.
Thank you very much for the introduction, and yeah, thank you very much also for the opportunity to speak here. So imaging and spectroscopy with photon pairs, that's the topic in my talk, and I will try in these 15 minutes to give just a rather broad overview maybe two methods how you can use photon pairs, so very specific quantum states of light, to maybe improve imaging and spectroscopy techniques. So in giving this overview, I will not really focus on the very details of things and not also on the details of particularly what we are doing. I will mention it, but not go really into details. So I am from the Friedrich Schiller University of Jena, in particular from the Institute of Applied Physics, and we are part of this upper center of photonics, which is a interfaculty research center here, which connects all the photonics activities in Jena and also all the activities then on quantum imaging, which is a stronger research focus here in the quantum part of the university. Okay, let's go ahead. Here we go. So photon pairs, first of all, we have to define what is a photon pair and how we generate them. So typically they are generated by a nonlinear process in a second or third order nonlinear medium, where we have, for second order nonlinearity, we have a pump photon impinging on this, and due to quantum fluctuations every now and then, one of these pump photons can split up into a photon pair, into two photons, which have then a lower energy, each of them, or a longer wavelength. And these two photons, they form a combined quantum state, which in general is entangled. So they share entanglement, which means that these two photons are not completely independent of each other. One could say that manipulating one of them has some effect on measurements of the other photon. And this is what we are going to use throughout these imaging procedures that I will detail in the following. But first, I want to go a bit more into detail in the properties of these photon pairs. So, because there are two typical conservation relations that have to be fulfilled, and that we are going to use then specifically. So again, we have this pump photons impinging on this nonlinear crystal. Signal and idler photons are generated out of this. And the first thing that always has to be fulfilled is energy conservation. So that means the energy of this pump photon is somehow distributed on the signal and idler photons, which means for their spectrum, for their frequency, that the sum of the frequencies of the signal and idler photon has to be the same as the frequency of the pump photon, which in turn means if here is a spectral axis, so if we know our pump frequency over 2, and we know let's say the frequency or the wavelengths of our signal, then we also know the frequency or wavelengths of our idler photon without actually measuring it, because of this energy conservation. If we know 2 of the frequencies, then we know the third, or if we can measure 2 of them, then we know the third. So this is one thing that we are using, knowing the frequency or wavelengths of one of the photons without actually measuring it. And the other thing that we are using is due to what's called momentum conservation, a conservation relation on the propagation directions of the photons, which is very similar. So if this pump photon has a certain propagation direction, then again, the vectorial sum of the propagation directions of the signal and idler photon more or less has to be end at the same point, which means that the signal and idler photons are propagating in very defined directions, where now we see that if one of them is propagating in one direction, then the other is propagating more or less in the other direction, which means this direction is closely connected also to a position. If we can measure the position, let's say, of this photon up here, then we know more or less the position of the other photon here without actually measuring it. So this is what we are going to use later on. One other thing which is very important for all of these measurements is connected then also to the statistics of these photon pairs. If we think about what is imaging or spectroscopy, it's all about measuring a certain intensity of light, either at a particular position or in a particular spectral range. Yeah, and typically if you have a classical beam of light, which is coming from a laser or just from a lamp, then these intensity measurements is fluctuating. So if you would do several measurements of this intensity, they would give you slightly different values. Yeah, and this is, for instance, for a laser beam, the distribution of these values is always looking like this curve given by the red bars here, which is what's called a Poissonian distribution. And you see that there's a certain uncertainty in this intensity coming from like the fundamental properties of the beam, the fundamental statistics of the beam. And with non-classical light, especially light where you know exactly the photon number of the inside this beam, so let's say for this photon pairs, you know it's always 2 photons, then this is getting much narrower, this distribution, because you always measure the intensity corresponding to these 2 photons. So you could basically reduce the noise in your measurement by using this known photon number. The question is how we can come to such a state, and well, again, this is connected to this photon pairs. Yeah, we always know these are 2 photons in each pair, and what we simply could do is we pump we use this nonlinear crystal. We are generating photon pairs. One of the photon pairs is detected without seeing any object. This is used as a reference, yeah, and then the second photon is used to illuminate our object, and we detect, of course, again after the object to see whether it passed the object or not in a particular point. And with this, we can measure the transmission or the intensity with a higher accuracy and can achieve a lower limit on this fluctuations that I detailed here, yeah, which is then called the Heisenberg limit compared to the shot noise limit, which is the classical limit. And this can be now used for imaging. What I showed here is this is pertaining to just, let's say, one channel, but if we want to do this in imaging, we have to do this on many pixels, and has been used a few years ago in this type of setup, where people basically use these 2 beams coming out of these nonlinear conversion crystals, these photon pairs. They put basically one object in one of the arms, imaged it on a camera, and then this reference measurement was done with the same camera, just in a different region of it. And then they got these 2 images, one where they had this shape of the object, and one where they basically could count how many photons actually were sent to the object, yeah, because the photon numbers here and here, they are connected. And if they subtracted these, well, they got a much better image than just the pure measurement. And they really compared this between classical light and this quantum light, and this comparison is shown now always in these 3 images shown here side by side for different parameters. And you can see, if you can compare them, this first one is basically always this classical measurement, and the last one is this quantum measurement. And this is now for very, very low photon numbers, so very small intensity. And you can see that this quantum measurement clearly is better than this classical measurement, in terms of that you can recognize the object there. Of course, it's not yet at the place that this is something that you could use commercially. So of course, if you use more light, you could get a better image. But if you are limited somehow in the amount of light, then this quantum method would give you the advantage that you have a better signal to noise ratio. That works well if you have a pretty high collection efficiency, so you need to collect at least 50% of all the photons, and it means it's best used for almost transparent objects. So you can go one step further. In this, you still needed like 2 cameras basically, or 1 camera that you distribute between this reference measurement and the other measurement. Go one step further to a procedure that's called ghost imaging, where again you split up these 2 things, these 2 beams for signal and idler. One is shown on the object, but after the object you just use a single pixel detector in terms of instead of the camera. And it turns out, by doing now a correlation between this measurement here, where you still have the camera, and this measurement here, where you have just a single pixel detector, you can still retrieve an image of the object, because correlation here means you measure the arrival times of the photons, because you know that the 2 photons of a pair always have been generated together. And basically here you can measure the arrival time of a photon if it passed through the object. And here you can identify to which spatial position it belongs, exactly because there's this correlation between the spatial positions of the signal and idler photon. So this was done already 25 years ago, roughly, for the first time. However, only very recently there have been actually cameras that one could use for this. So back then it was done with scanning detectors. And this is a more recent example where basically the object was placed in one arm here, measured with a single detector, and the reference photon was measured with a camera, where they showed that in this ghost imaging configuration with a few, let's say, thousands or 10,000s of photons, you could measure images of very simple objects, whereas if you use the same photon number but with direct imaging, well, none of the object was actually visible. So this is again a better signal to noise ratio in this, let's say, quantum imaging configuration, and a slightly worse image in the normal imaging configuration. And they used it also for more, let's say, applicable objects, like here's a wasp wing, for instance, which they imaged with a few hundreds of thousands of photons, which, I mean, is a big number, but is a very small energy, and in every normal imaging configuration, you would have much more photons. And another advantage of this technique is now that your camera that you're still using, that this can be at a very conventional wavelength, let's say in the visible, where you can easily get cameras, whereas the other photon could be also in the infrared, where you may not have a camera, but still have a single photon detector. And this is an example where the same group in Scotland, they showed exactly this. So they had an object which contained gold and silicon, and in this infrared wavelength range where they illuminated the object, well, the silicon is transparent, the gold is not. In the visible, both of them are non-transparent. So, and they basically could image the properties of this object in the infrared wavelengths by doing images in the end with a visible camera, which they reference to these measurements of the infrared photon of a single detector. So in everything what I showed to you, well, you still needed this particular single photon camera, which is, well, a very expensive device. What we are currently looking at, and also other groups, is how we can go back to a scanning configuration, but still do this in an acceptable measurement time. So this is one example where people showed that this is working also for scanning imaging. So they again have these photon pairs here, one detector here, and the other photon is going through the object at one place, still measured by a camera for some technical reasons, but they are scanning the sample and see the same thing. So at each point, they do know this measurement technique and can retrieve the object with a resolution of about let's say 2 to 3 micrometer, but that depends on the microscope objective. But still, their measurement time per pixel is in the range of 1 second. What we are currently trying is couple this with really a scanning optical microscope, where basically one of the photons is sent to this microscope, where we have a normal these scanning mirrors which move the beam across the sample. And we hope that with this technology, we can bring this quantum imaging to a regime where we can make an image within a second, or in the order of a second, limited basically by our photon pair source. So you need a very efficient photon pair source, which gives you a lot of photons to do this. But we are optimistic that we can achieve this. Well, all that I explained you up to now, that was pertaining to imaging, so measuring spatial information. You can do the same thing also for measuring spectral information, using basically that there's also this correlation between the wavelengths or the frequencies of the two photons. Yeah, it's a very similar setup. You split the signal and idler photons, put the sample in one arm, but there you measure just with a single detector, and in the other arm, instead of the camera, you put a spectrometer. And do the coincidences, and the spectrometer could be now again indivisible, whereas the other arm could be at any wavelengths where you have a single photon detector, and you can measure spectra with this setup. And what turns out is that it's also more tolerant to noise. yeah, because you have this additional reference of the second arm. So if you have noise in one of the arms, this will not affect your measurement as much. Maybe summarizing this first part about the ghost imaging, it's a technique that has a few advantages. Yeah, it allows you to overcome the shot noise limit. It reduces the sensitivity to stray light, and it improves the detection in challenging spectral ranges, because you do not always need a camera for the wavelengths where you actually want to measure, but you still need a single photon detector. On the other hand, it's also it's technically very challenging. Well, because you need single photon detectors for each wavelengths that you want to measure, and the performance is in the end very sensitive to losses. And to really make it applicable, well, I think still a lot of development on this detection side is still needed. Yeah, so in particular, we need cameras that can do single photon timing, so like these SPAD arrays, which are under development in several groups up to now. We need efficient single photon detectors for infrared wavelengths based on these nanowires, most likely. And well, you need very efficient optics for all involved wavelengths to meet this loss condition. Yeah? So I think there is an application for this, but it needs to be some development on various fronts to come to a regime where it is really applicable. I want to present another technique which is a bit closer to application, in my opinion at least, and still also has very nice properties. And this is based on an effect called induced coherence, where now we combine two of these photon pair sources in something which is can be viewed as a nonlinear interferometer, and we have basically the signal photons coming out of these things are interfered in one detector. This is everything that's measured. And we can put an object here in the arm where the idler photon of one of the first source is passing and then going into the second source and overlapping with the idler photon coming out of the second source here. And it turns out that the transmission of this filter put here, so this was the first experiment showing this, that this transmission of the filter, that this influences the visibility of the interference fringes measured here in this detector. So the visibility, by measuring the visibility of these fringes, one can measure basically the transmissivity of this filter, although you never measure the photons that interact with this filter. This is shown here. So if there's no filter, well, you get interference fringes if you move this mirror here. If you put the filter or totally block the beam, well, you don't get any of these fringes. And this can be used also for imaging. It works, of course, for different wavelengths of the signal and idler photon. And can be used for imaging, or was used for imaging a few years ago for the first time. So where here you have these two sources, these are the two nonlinear crystals. In the middle is the object which interacts with one of the wavelengths, this red beam, but this one is actually not measured in the end. And the idler photons coming out of both crystals, so these yellow wavelengths, they are interfered and then detected with a camera. And well, in that they just used a cat, because they are physicists, they always look at cats, and could measure the image of this cat, although they never measured the photons that actually interacted with them. Yeah, and this principle works in a very broad spectral range up to the terahertz. There have been some recent publications looking at this, where they did terahertz measurements by doing actual imaging in the visible only. And there are a few very nice examples showing that this is already quite close to applications. So one is done in Berlin, actually, in the group of Sven Ramelow, where they did microscopy in the mid-infrared, showing that they could do imaging at wavelengths around 4 micrometer. Actually, by changing the properties of their setup during the measurement, they can change the wavelengths and can do something like multispectral imaging around this. And they showed this for a mouse heart, for an object which was a mouse heart, so some biological sample, that this is applicable to let's say real life samples. And it's still working with very small photon numbers, so around 5,000 photons per pixel per second, then on the object, which is a very small number. This is also a scheme which works in video rate. So this is now from Jena, an example done at the Fraunhofer Institute, which is also part of the epicenter of photonics, where you can see here a live video basically of an object moving in such a setup where, again, the measurement, like the photons hitting the objects are in the infrared region, and the measurement is done in the visible, with a resolution in this case up to like 60 micrometer, but this is limited mostly by the optics. And again, this can not only be used for imaging, but it can be used also for spectroscopy. So this is another example where people build a Fourier transform spectrometer using this measurement principle, so nonlinear crystal. The photon pairs are split. One of them is going through the sample, coming back. The other one is not interacting with the sample, also coming back. And here the interferometer is actually built. Sorry, I forgot to mention this also for this earlier experiment. So the interferometer here is built by using the same source and basically going back and forth through this one nonlinear crystal. Yeah, and then the signal is imaged, or here it's not imaged, it's just measured with a single detector, and this mirror is moved to measure interference fringes. And what they could show is that they could measure a very high resolution spectrum of methane and absorption spectrum at around 3.5 micron by actually doing the measurements only in the visible spectral range. So this was a normal photodiode silicon photodetector, which can measure only in the visible spectral range. Yeah, so, and that achieved a spectral resolution below 1 nanometer, which is quite good, by using only 20 nanowatt of illumination power on the sample, so could reduce the power. So, and also to summarize maybe this as a second method to do imaging and spectroscopy with photons. So here you don't need any detector in this challenging spectral range that maybe you want to look at. So all the examples were in the mid-infrared. It still reduces the noise because usually detectors for this mid-infrared spectral region, they are very complex and, well, in the performance still not, let's say, very good, at least compared to these visible detectors. And since it's an interferometric scheme, it can also measure the phase, not only the intensity. Well, also has a few challenges, mostly technical. It's an interferometric scheme. It's limited in the spatial resolution that you can get due to the sources. Yeah, this is actually the thing that mostly still needs to be developed. Yeah, these sources for particular this scheme, and it's now sensitive to stray light because it doesn't use this let's say correlation between the signal and either photons that was used in the ghost imaging. So with this, I am at the end of the talk. So I think, well, I hope I showed that these photon pair-based measurements can have or are promising for different applications in maybe where you can use these complicated spectral ranges, especially in the mid-infrared. So for instance, in medical imaging, infrared spectroscopy, and another example that I did not discuss was in CMOS quality control, where people showed that you can use these imaging principles, but to actually come there, and I mean, all this were lab kind of demonstrations, to actually come there for real application, what we need is to do a little more work on the sources. We need higher brightness sources, but and also sources which have more, let's say, modes to get more information, more pixels, more spatial resolution. And on the other hand, especially for this ghost imaging, we need we need better detectors, single photon detectors, and single photon cameras. With this, I'm done. Thank you for your attention, and I'm happy for questions.
Yeah, thank you very much, Frank, for this brilliant talk. So there are already 2 questions, and I want to encourage you to use the Q&A box to ask your questions, and the speakers are also able to answer the questions after their talks. So the first question for you, Frank, for the ghost imaging, do the longer or shorter wavelengths photons define the resolution limit?
So unfortunately, it's the longer photon. So you cannot get, let's say, enhanced resolution with this, and this is due to the fact that still, I mean, physically, what limits the resolution is that that plane waves cannot propagate in free space beyond a certain wave number, so they cannot simply transmit information which is too hidden in too small features. Yeah, and in this ghost imaging, still we have to do this propagation in free space. If we go to one place where we have the image here, so you still have basically to transfer the information about your object from the object, let's say, to the detector, and that in the end limits you in the resolution to this longer wavelengths, or to the wavelengths which is interacting with the object. Let's put it like this.
Okay, thank you. There's a second question for you, Frank. For reducing detector noise, do you have a plan to use some method in deep learning, such as autoencoder?
So, I mean, we are thinking about this, but up to now we did not really start, and we are not really experts in this. Yeah, so I think that could be really helpful, especially in, I mean, if the aim is to do imaging with very small photon numbers like here, yeah, there will be always the challenge of making a nice image out of these type of things. And there we believe that computational schemes could help us, but we are not really experts in this up to now.
Okay. Yeah, maybe the one who asked the question could tell you more about this. So I'm happy to introduce you.
I would be really interested, yes.
Okay, perfect. Sounds great. Okay, yeah, then thank you again, Frank, for your talk. And yeah, you will be available for future questions in the Q&A box.
Sure. Then I will stop sharing. Go.
Okay, yeah, then thanks again. And then we can go directly to the next speaker. The next speaker is Dr. Markus Kudzik. He is head of the Joint Lab Integrated Quantum Sensors at the Ferdinand Braun Institute. And I'm curious to hear more about compact atomic systems for timing and sensing applications. So Markus, the virtual stage is yours.
Yes, thank you, Johannes, for the introduction. And yeah, first of all, many thanks for having me and for the opportunity to talk to you here at this QBN webinar. So yeah, my name is Markus Kudzik. I'm working now since a little bit more than a decade at Humboldt University with some on and off time, and now recently started additional activities at the Ferdinand Braun Institute. And today I would like to tell you or give you a little overview on atomic systems for timing and sensing applications, with the goal of pretty much similar to Frank, give you a broad overview on what atoms are capable of sensing for, and B, tell you a little bit about what we are doing in Berlin. And in the background, you already see one of our experiments, and those of you who work with atomic lines may guess now that by looking at this blue color and a little bit red here in the center, that this has to do with strontium atoms. And indeed, this is a setup for a Ramsay-Baudet matter wave interferometer, which we built up for a very compact but still precise optical clock. But yeah, let me start a little bit by just introducing quickly our joint lab for integrated quantum sensors. So joint lab, as the name says, is a joint laboratory between two institutions. So one is the Ferdinand Braun and the second one is the Humboldt University. And it was established in the beginning of 2019 with the goal of developing compact and robust atom-based sensor technologies. So we are totally fascinated by all the wonderful things you can do or you can sense with atoms. And this is what we investigate and research at the university. And we have a strong partner with the FBH to put these sensors and actually into application and into practice for frequency timing, field sensing and communication applications. But before I give you some examples to underline the importance of atomic sensors to our perspective, let me remind you of the basic principle, or the modus operandi of such an atomic sensors, or at least how we see this. And in our case, it all starts with laser, or more or less more than one laser, so lasers, which we use to initialize, to coherently manipulate, and also to read out our atomic system, which in a sensor is brought into a very controlled interaction with the environment we want to sense, which could be electrical fields, which could be magnetic fields, it could be the gravitational field, or it could be no field if we want to map out and precisely measure the intrinsic properties of atomic transitions for optical clocks, for example. Then we have some sort of detector who is, or which is able to measure the internal and or external degrees of freedom, such as, for example, we want to measure the reaction of the atomic transitions, or one atomic transition to an external field. Maybe we have a shift of this internal transition, which we want to measure, or the external degrees of freedom, where we literally move the atoms and transfer momentum to the atoms, and then read out this in our sensor. So this detector then is either directly analyzed or fed back to the laser, displayed, and here we go with our sensor application. And here on the on the lower right-hand side, you see one application of an atom-based sensor. In that a picture, you see a temporal sequence of density distribution of ultra-cold atoms. So these are atoms which are cooled down by lasers and additional methods to temperatures only a billionth of a degree above absolute zero. And then we can follow the trajectory of the atoms where they undergo a so-called Mach-10 interferometer, which you may know from optics. So when you have a light wave, a coherent light wave, which is coherently split, redirected, and recombined, and you read out the interferometer fringes to build up some certain type of sensor. And here in this picture, we do not use light waves, we use atomic matter waves for our system. And as you can see in the far field, because the origin is in the upper right and it goes down to the lower left, you see spatial interference fringes appearing also for this matter waves. So we can build sensors out of these atomic waves. But there's more you can do, and you do not even need to have cold or ultra cold atoms. So here you see why we are also fascinated by atomic sensors, because there's really a diverse spectrum of applications based on these systems. So here you see a little chart, which I took from Dave Anderson and modified it a little bit, which shows you the physical quantity and the type of quantum sensor 1.0, 2.0 you can use to measure this physical quantity. Of course, you can measure time with atomic clocks, where you stabilize a laser onto a very narrow line with transition of an atom. You can measure accelerations and gravity by following the trajectory of freely falling atoms in a so-called atom interferometers, which you can use, for example, to improve your knowledge about the geoid, to improve climate change models in geophysics. You can use atoms to build magnetic field sensors, so-called atomic magnetometers, for biomagnetic field sensing, for example, or you can use very loosely bound or highly excited Rydberg atoms, which are very sensitive to external electric fields, to build electrical field sensors. And when you look at all these applications, of course, right now we are at the edge of pushing them into real world applications. I mean, it has been demonstrated in many, many places in the laboratory. There are already companies and startups working towards this. And yeah, we in Berlin, we have some certain focus on putting these technologies, or let's say enabling technologies for these sensors in space, to prove the robustness, to prove the automated operation and the reliability of our system, with the hope to address certain applications in space, but also to spin off again from space to ground-based applications. So here you see a little overview, which I will not go into detail, about laser module technology, about very compact, robust, narrow line with high power diode laser based systems, specifically for atomic spectroscopy, which have been developed at FBH since also now more than 2 decades. And we see here laser systems composed of course, laser sources, electronics, optomechanics, put into robust packages such that every one of us can, or in principle, everybody of us can operate them and send them to space. And the goal here is, of course, to use the high sensitivities of quantum sensors for Earth observation application, to use the stability of atomic clocks to improve GPS or GNSS, and also, of course, to address fundamental science. And yeah, currently we are looking at very compact systems to be also put on smaller and smaller satellites, and that's also worldwide activity, because it means that you can cheaper and more repetitively launch these systems to space. And yeah, I will guide you to some examples to kind of elaborate what is able or what is maybe state-of-the-art technology and what one can do in the future. So here you see an example of a rubidium-based optical frequency reference where we use a laser which is mounted here. You actually don't see it on a micro bench with some micro optics to guide the laser beam into a small vacuum cell or a vapor cell, which contains rubidium vapor. Then we use here Doppler-free spectroscopy to stabilize the laser to some of the transitions in rubidium and guide the light to the application, which, for example, could be an absolute frequency reference for navigation or for calibration of your optical devices. We integrated them into 1U CubeSats, and yeah, we are at the stage of really using these hybrid micro-integrated frequency references also in other applications out of space. Another example I was already sharing at the beginning are meta-wave interferometers, where we really use the fact that we can coherently split and recombine atomic meta waves for some sensing applications. On the lower left, you see one of the topologies where one can use an atom interferometer, a so-called Ramsey-Baudet atom interferometer, where if you believe me, you can follow several trajectories of our atoms, which are entering from the left-hand side, then being split at 4 laser beams. And then here where the blue circles are, you actually see that a recombination of the meta waves happen. And in the phase or in the interference pattern we actually record in the end, we have encoded the information of the phase difference of the 2 different arms, which depends on maybe rotations, on accelerations, or other external influences. And yeah, one of the key technologies, one is looking here. I mean, I already mentioned lasers to be very important for atomic sensors. It is also the atomic source itself. So that could be either some dispenser or some high-performance oven system, as you can see here. So this will also be important in the future, that we have compact, robust, energy-efficient atomic ovens, which give you certain specification of atoms to enter your specific experiment. Another example here is an experiment led by University of Hanover, where we're also participating, which generated the first Bose-Einstein condensate in space and did proof meta-wave interferometry in space. So on the right-hand side, you see it's actually a sounding rocket. So you have to imagine it as a maybe 15-meter height rocket, where the experiment is actually in a length of about 2.5 meters. And this experiment is then sent to space, operates there for around about 15 minutes before it re-enters the atmosphere, including ascent and descent. This experiment runs totally autonomous, produced laser-cooled atoms while the rocket has been spinning, generated a BEC close to the apogee of our parabola, and then, as I said, also proved the capabilities of meta-wave interferometry in space, which brought the vision of using these type of sensors also in other industry-based applications maybe one step closer. Important for space-based applications, but also for everything you think on ground are, of course, enabling technologies. One focus is, of course, on micro-integrated and miniaturized optical setups for atom trapping and manipulation to build really integrated atomic sensors. There are many points one has to address. One, for example, is here to build smaller and smaller optical distribution system. You can either do it fiber-based, you can either do it in a hybrid fashion or totally free space. For the latter, you have to investigate bonding technologies which are vacuum compatible, which are scalable, which are maybe also cheap and fast to be done. And this is also one of the aspects people are looking into, to say, okay, I have a vacuum chamber where I have my atom manipulation and all the optics and lasers and electronics are around this chamber, or I try to put everything in the chamber and therefore miniaturize. Another example, I have two more, including this, are optically pumped magnetometers. So here you see some publication from NIST, from John Kitching's group, where they demonstrated a small vapor cell-based optical magnetometer, which is based on the collective coherent precession of spin polarized ensembles. Here in the background picture, which is taken from University of Nottingham, you see already these OPMs used to map out human brain activity. So the goal here is, of course, the non-invasive measurements of biomagnetic fields for improved and personalized diagnostics. There are a couple of spin-offs already working in this field. And yeah, it's also very fascinating and also depends on atoms, vapors, and atomic spectroscopy techniques. And similar, this is the last example, what you can do with atoms is radio frequency electrical field sensing or field strength measurements using Rydberg atoms. It's also a spectroscopic technique where you have two laser beams which are coupled together, and then you have some RF source, which then basically couples to a Rydberg level here, and you see the strength of the RF source or of the external field, because it basically changes the spectrum, the AIT spectrum you see in your system. So it reduces the absorption of the probe beam, and with that you can measure from very low to very high field strength, also in a very interesting bandwidth. So for high frequency calibrated field probes for next generation wireless communication calibration or radar. And for this to come back to also the origin of what Frank at the beginning said, that Berlin is, of course, a strong region for photonic technology. So here you see the typical requirements for quantum sensing applications by the example of strontium, but that's very similar to other atoms. So you need to have lasers working in this spectral range from visible to near infrared, line widths from megahertz down to hertz when you have very narrow line width transitions. The powers are usually from milliwatts to watts. You need to have some certain tunability and repeatability, and all of that needs to be integrated into, of course, high robustness, reliability, low mass and volume, energy efficiency, and modularizability in terms that you can really scale up on the technology you're using here. And yeah, that's why we also started a little regional network to investigate together with companies, industry, universities, research institutions, the needs and the requirements on certain applications, and therefore have a coherent set of requirements one can target the technology development to. Okay, now coming to the summary. So yeah, I did tell you a little bit about compact and robust atom-based sensor technologies, which are quantum tech 1.0 to 2.0, depending on how you look at it, from Doppler-free spectroscopy to matter-wave interferometry, from really hot, warm vapors to cold and ultra-cold atoms. And the applications are really very, very broad. And this is something which is fascinating about this field. It goes from frequency reference to clocks to inertial sensors, velocimeters, magnetometers, field sensors, even to ranging. And right now we focus on mobile applications to go out of the lab and even to space. Another thing just mentioning at the side is when we look at the technology development roadmaps, I just want to emphasize that atomic packages, which we need to have here for sensors, they're also needed in other fields of quantum tech, in quantum computing, of course. There are architectures based on cold atoms, ultra-cold atoms, and quantum key distribution or quantum networks when it comes to quantum memories based on atomic vapors and so on. So there are strong EU worldwide efforts. I think, in parallel to system level verification, it's the old argument that one should also focus on enabling technologies in parallel, and this very strongly. So we need to have R&D programs on all the key technologies from laser to vacuum to electronics, but also validation facilities and system integration to in the end prove your sensor development. And in the end, of course, we should be able to cover the full value chain from chip to system. And I'm thinking we are in a good position to achieve that. And with that, I acknowledge the entire team and thank you for the attention.
Yeah, thank you very much, Markus, for this great insights into your great work. So There's one question, what is from your point of view necessary to develop real products, or is it just engineering?
I mean, it's just engineering is already the wrong phrase, I would say, because it's not only just engineering. It's I think it's clear that if we want to have these applications based on, let's say, atoms, I mean, speaking about vapor cell applications, to have it in a cheap and mass productive way, that we have to transfer most of the technologies onto a wafer level based technology. We need to look at hybrid system, at integration on chip level. And for this, it's there's really a big step we need to go all together, because right now we have been proving that we understand the atomic physics, the quantum physics behind the application fine. There are many examples where people put in demonstrators meaning maybe it's as big as a 19-inch rack you can move around, or as a backpack and so on. But I think this is still one order of magnitude too large. And really, if we want to go into mass producible atomic sensors for a certain type of application, we really need to follow the path of chip level integration to really have these small and compact devices. And this, now I come back to my first assessment, is not only engineering, because it also requires knowledge about how our atomic systems are reacting to the environment. I mean, I said this is the basis of a sensor, but when I integrate and shrink down the volume, the atoms will see electronic circuitry, the atoms will see some sort of environmental potential. And maybe this requires us to also rethink ways of do spectroscopy, or maybe it changes requirements on the interferometry topology we use, because the atoms, they are so sensitive. That's good and that's bad at the same time.
Yeah. Okay, thank you very much. Yeah, for the moment there are no further questions, but I think you are also available for further questions.
Yes, I'm happy
here for the next minutes. Okay, yeah, then thanks again, Markus, for this great talk, and I'm very happy to welcome Matthew Malcolm. He is Principal Research Scientist at Element 6, and he will tell us more about engineering diamonds for quantum sensing.
Thank you. Oh gosh. Yeah. So yes, I'm Matthew Malcolm from Element 6, and I will be talking about engineering diamond for quantum technologies. Working. There we go. So just to give you an outline of what I'm going to talk about today. So I thought I'd start with just a sort of perspective. Obviously, this is a meeting about Europe, so I thought I'd give a bit of a perspective on what I think about sort of diamond quantum technologies in Europe. I'll then go on to talk about diamond quantum technologies, what it is, and how we do it, and the application space. I'll give you a brief overview of how we make our diamonds, and then sort of go through a case study of our synthesis and characterization work to develop a diamond for particular applications, but looking at the sort of how we can scale it, how we can sort of really engineer it to make it a useful product. And then I'll finish up with just a brief summary of some of the other materials we're making, both commercially and also in R&D. So growth in diamond quantum technologies worldwide, I'll start with the bigger picture. So I've actually been very fortunate that I've been working in this field now since 2007, and this sort of little cartoon map shows some of the expansion of diamond quantum technologies over 10 years, from 2007 to 2017. And it has been very rapid, a lot of growth, and that's I think in part due to the networks and due to the collaborative nature of many of the people that started out in the field, helping and supporting other groups to develop. I think there's also an element where I think hopefully our diamonds has helped enable some of that growth. So the initial work done in this field was actually done on a natural diamond, a single natural diamond, which was cut up and sent to various groups around the world. But obviously that's not scalable. We introduced our electronic grade diamond to the quantum market around sort of 2007, and that then acts, and the diamond really is the heart of any of these quantum devices, and that has obviously helped many academic groups around the world, but then also now industrial groups build on the understanding of diamond quantum technology, and also start to transition that into commercial devices. And I think there's three components to this sort of network, if you like, and I think it really is a partnership between these three things. So funding, so the funding agencies, academia and industry. So starting with funding agencies, obviously there's lots of programs worldwide. This map here just shows you some of the investment that's gone on worldwide on individual programs in various different countries. And so I've just got the Horizon 2020, which we've got 3 projects that we're involved in at the moment, as well as UK RI and Innovate UK funding, which is another UK funding body. But as I said, there's obviously lots of funding bodies in other countries as well. And basically, what that's done is basically put a lot of money into academia, and these are just some of the groups that we work with. And I apologise for not listing all the groups we work with, because there's quite a few of them around the world. But these are sort of some of the main ones we've interacted with over the years in the diamond quantum technology area. But then what's happening now, and I think this is really key, is a lot of interaction between academia and industry. And I think that's key, and it's happening at several levels. One level is just straight technology transfer. So that many groups are working directly with industry to help support spin out this technology, either through direct spin outs, so startups that are taking technology that's been developed in universities and then moving that into a new company, or established companies that are going, look, we see there's something useful, let's work together. And a lot of academic groups are really working hard together with industry to make that happen. But then it's about the people and the training, so they also provide sort of the support for that. And we see that a lot in the diamond quantum technologies area. I think over the past 5 years, there's been a massive upsurge in the number of companies, not just developing the technology. So companies like Tsunami, who are talking later, Thales, Envision, Bosch, these are all companies that are developing the end technology, but there's also companies that are also, like ourselves, developing the components. So like Anima 6, we're developing the diamond. Companies like Toptica, for example, developing laser systems for specifically made and engineered for NV quantum sensing and quantum communication. So that's just a brief background of my thoughts on the advantages of the sort of the network that's established in Europe around diamond quantum technology. So now, what is diamond quantum technology, and why are we interested in it? So most of it's all based around a particular defect called the nitrogen vacancy defect in diamonds. What's particularly unique about this defect is it effectively behaves like a trapped atom, but in a crystal lattice. And so you have this interesting energy level structure such that when you just shine green light on the defect, you can spin polarize into a ground state, and simply by application of microwaves, you can flip that state into a state which is sensitive magnetic field, or you can put it in superposition depending on what actually you want to do with it. And then the readout process, exactly the same. You basically fire green photons at the MV defect, and the amount of red luminescence you get depends what state you're in. And we can see that in this plot here as we tune the microwaves. Once we hit resonance with this transition here, we get a dip in the fluorescence coming out. Optically, it's called optically detected magnetic resonance. And when we apply magnetic fields, this is what we've got going up here, we get a Zeeman splitting, which is determined by these fundamental constants, allowing you to make, for example, a magnetic sensor. The other big advantage of this quantum platform is that all the technology is pretty simple. No complicated detectors required. You can build a very crude system using effectively a laser pointer, a diamond, magnetic field, RF source, and a detector. So you've got this basic base platform. You've got this base material. What can you do with it? lots of different applications. Most of the work that I'm going to talk about later, the material I'm talking about, is for bulk magnetometry. So that's using lots of these NV defects to sense very small fields. You can do other things, for example, have much higher purity material to do things like nanomagnetometry, and that's something I think Kunami will be talking about later. And you can also sense other things other than magnetic fields, things like temperature or electric fields. So you've got this great platform to act as a base for developing lots of different types of sensors. So how do we grow the diamond? So we use a process called chemical vapor deposition. There are other techniques to grow diamonds, such as high pressure, high temperature. We do that as well, but the reason we use and choose to grow our quantum diamonds using chemical vapor deposition is you have much more control over the sort of the concentration of defects you're putting in. You can also much more easily tune things like the isotopic concentration of the various constituents, so the carbon or the nitrogen. So in CVD, we use a chamber, and this cartoon here sort of represents the sort of chamber into which we add a couple of gases, two main gases being hydrogen and a carbon-containing gas such as methane. We then inject microwaves which break up those gases into sort of into their sort of atoms, exciting this gas, and that's very key to basically this process here. And what we can see, the white blobs here, these are our hydrogen atoms, and they play a key role. Firstly, they terminate the surface, stops it reconstructing into graphite. They also create the methyl radicals, which then attach onto the diamond as well as the site. So it's playing a very, very key role. And basically, by tuning the various different properties or the process, so the pressure, the temperature, the preparation of the surface, you can really change and manipulate the material you grow. And obviously, you can choose to add nitrogen to the process as well and tune that nitrogen depending on the resultant diamond you want to grow. And this little video in the bottom right here just shows you the growth, a speeded up image of the growth of the diamond. So we need to consider all these factors when we're growing diamond. And so what are the actual factors that we want to actually manipulate in the material itself? Well, ideally what you want is something with a very long T2 star, so spin coherence time, having a long spin coherence time. You also want all your emission, if possible, to be from the negative charge state of the NV defect. You do have always the NV0 defect, which will also emit light, and that basically affects your contrast. So the amount of light, the difference between the sort of the the plus or minus 1 state and the 0 state, you get this sort of a contrast which is limited by the background light that you see, as well as the diamond geometry. So you want to get the light out of diamonds, so that's also an important factor. In an ideal world, you want to maximize your NV or N concentration, if you like, to get the most number of defects for things like the bulk magnetometry. But this is actually competing against T2 star as you increase N. In this plot, you can see it here. As we increase N, we reduce our spin coherence time, and there are things we can do, such as make it isotopically pure. So this is the blue line here is when we make it isotopically pure. But there's always this trade-off in device. You have to think about how you're going to make a system and how you're going to link all these components together. So the material that I'm going to talk about today roughly sits around here. So it's about 16 ppm nitrogen containing diamond, which is, as I mentioned before, very useful for bulk and magnetic sensing. So how do we go about doing that? So our sort of process, if you like, and this I'm just going to talk through our process that we have used to grow our high nitrogen material and sort of the methodologies we use to sort of narrow down on a recipe and then turn that into something we can productionize. So with our high nitrogen recipe, what we did was start growing relatively thin layers, sort of 100 micron layers on moderately or lowly doped CVD substrates. That then allows us to do relatively quick synthesis, and you have to do short loop experiments where you can grow very different parameters and then quickly build up a picture of what those parameters, the effect those parameters have on the material you're growing. And one of the things we started this work was we wanted to reduce the number of parasitic defects in the material, but we wanted to maintain our nitrogen concentration because that's what we want to convert into our NV defects. What we can see in this image here is a series of samples we've grown where we've varied some process conditions. And what you can actually see, you can see this sort of brown coloration, which is indicative of things like vacancy clusters or NVH, other basically parasitic defects in the material. But by carefully tuning and changing the conditions, we're able to reduce those defects. And interestingly, at the same time, we actually increase the amount of nitrogen in that material and reduce the parasitic defects, showing that there's this, for high nitrogen material, you don't necessarily need to lead to increased parasitic defects. So based on this particular work, we then want to focus down further by growing a few samples. We were targeting around 16 parts per million nitrogen. So we basically benchmarked 3 different processes, these 3 different recipes here, and we grew them to much thicker layers now. So we're growing 600 microns rather than about 100 microns, and that allowed us to do more measurements to look at things like the charge state of the nitrogen in the material. And then we use that to then monitor what that charge state doing. And that's important for looking at, because basically that charge, any positive nitrogen, that charge is going to something that we don't want there. So any NS plus is basically a bad thing because that charge is not being used to create your ND minus. Both for the device and the recipe, we settled on this particular recipe here, recipe 2, where we got 16 ppm, and then we of nitrogen, of total nitrogen in the material, and that works out about 13.1 NS naught. And what we can see in this plot here, we're able to grow a batch of material where we've got a very good uniformity of nitrogen in that material across a number of samples. The next thing is we want NV in that material, so we need to create our NV defects. We've got our nitrogen, so we can create vacancies by irradiating the diamond with electrons. And so this plot here just shows us mapping that out. So using optical absorption, we were able to measure the GR1, which is the neutral vacancy concentration in some witness samples. So these are just low nitrogen doped material. So there's not much ND1, which is the negative charge state of the vacancy. We then picked a particular process, a particular vacancy concentration. And then this also then just another thing that's also key when we're engineering diamonds, making sure that process is consistent. And this is basically a series of runs over a period of a year where we treated a witness sample and measured the amount of neutral vacancy in that material over that period, showing we've got a consistent process with less than 4% variation between runs. So now we've taken our radiation process, now we apply it to our material to create our NV. And so this is a batch of 24 samples where we applied that to, and monitoring both NV minus and NV zero. It's important to comment that actually when you do that measurement, there's quite a few nuances in that, in the sense that you can actually shift this charge around depending on how you treat the sample. And so that'll be slightly different when it's using an actual device. But what we've done here is basically apply UV treatment to put it into a particular charge state before doing the measurements. And then what we see is we get roughly about 3.8 ppm of total NV with less than 4% variation. So we've got now a very controlled material. So what else is important? So T2 star is obviously an important thing, but one of the big factors that affects T2 star is the strain in the material. So monitoring the birefringence, we found being quite critical to the process. So this is a set of 6 different samples where we've measured the birefringence. So diamond, it's a cubic material. It shouldn't have any birefringence. The birefringence comes from dislocations in the material, so you need to be able to control that, the dislocation concentration, and that we found is actually relatively tricky for this higher nitrogen material. But we found these conditions where we're able to grow this material with relatively low birefringence, so something around sort of sub 10 to the minus 6. How does that translate into straining the material, and how does that affect T2 star? Well, this is some measurements that are performed by Ron Waldsworth group at Maryland, where they can do a strain shift map. So this basically is looking at effectively the ODMR line position and then looking at that across a sample. So this is 500 microns here. So this is basically across a 3x3 samples, and these are also similar size 3x3. And from what we get there, we get a strain spread of about 25 kilohertz across all these samples. We have this very low strain material. So then the final thing, the final material is this nice purple material. And when we do a T2 star measurement of that material, we see a T2 star of just over a microsecond, which is what you'd expect on that plot I showed you earlier of nitrogen versus T2 star. We're at where we'd expect it to be, i.e. there aren't other parasitic defects in the material which are limiting the spin coherence time. And this is all written up in this paper that I've referenced at the bottom. What's important is that basic process that we've gone through there to help engineer the diamond, and we do that for other materials at different concentrations. Now, it'd be lovely if I could just turn the nitrogen concentration and it just, I can pick our nitrogen concentration. Unfortunately, it doesn't work like that. Every time you tweak your nitrogen concentration, you affect some of those other parameters that I started talking about, things like the strain in the material, and therefore you have to go through that process of changing the conditions and developing the conditions for particular recipes. So I've talked particularly about this 16 ppm material. As I mentioned at the start of my talk, we do a range of other materials, and we are doing a lot of development work looking at new materials. So we launched a material called DMVB1 last year, which has a much lower concentration. So using it probably a slightly different way to our 16 ppm material. I mentioned single MV defects. If you want to do single MV defect work, then our electronic grade diamond is a sort of useful material for that. And then we do other things such as taking this type of material, this high 16 ppm material, and putting it on top of our electronic grade diamond to make thin layers. And that's useful for things like imaging magnetometry. So just to finish, hopefully I've shown you that CVD diamonds is a powerful method to create material for diamond quantum technology, showing long decoherence time at room temperature with this optical initialization and readout, which is relatively easy to do, which is, I think, why we're seeing a lot of growth in terms of industry now picking up this technology. E6 has developed a range of materials to help enable this area in both areas such as quantum computing and magnetic sensing. So that is the end of my talk. It just like to say thanks very much for listening, and obviously please contact me if you've got any questions, and also thanks very much obviously to the funding bodies and also the various university groups that we work with in Europe and around the world. So if you have any questions.
Thank you very much, Matthew. So diamond is definitely a very great material and enables a lot of quantum technology applications. Yeah. So there's one question for you. How important is a good coupling for readout and manipulation of NV centers in the whole development of a sensor?
So about the coupling out of the light, is that?
Yeah, right.
So yes, I think it is very important. I mean, often when we work with many industrial partners and also the academic group, it's thinking about the system. So you can't think of the diamond as a separate thing and go, we'll make the best diamond, and then you have to think about how you get that light out, because a lot of that light can be wasted. I mean, in some of the simple demonstrations, you can see lots of red luminescence coming out and going to your eye. that means is obviously wasted light. You've got to find ways to capture as much of that light as possible. So I think that's very, very key to, well, it's key in how we work with people. We try and work with partnership with people to help them come up with structures and things that to enable that coupling as best as possible.
Okay, in this case, was state of the art if you think of very small sensors, or is this just a thing we have to improve?
Yes, exactly. Yeah, I mean, you can do some quite impressive processing when you we've made some shape parts, for example, which say 300 microns by 300 microns with particular angles. You can do that. I mean, in some ways, you have to think of I often point people towards melee diamonds, very small diamonds. You can put a facet on a small diamond, and in similar ways, you can make a very bespoke parts for quantum sensors to allow you to couple the light out.
Okay, yeah, thank you very much. Okay, you will stay also here in the audience for further questions.
Yes.
Okay, thanks again, Matthew. Then we will come from material directly to the applications. And I'm very happy to welcome Matthew Munch. He's CEO of Qnami, and his talk is about supporting the emergence of new computing technology with quantum metrology.
Yes, thank you, Johannes. Good morning, everyone. I'm going to share my screen. All right, hopefully this is coming through. All right, yeah, so it's my pleasure to be here in the Quantum Business Network. I wanted to take this opportunity to present a bit Qnami, what we aim at, and in particular highlight how we think we can, through the support of quantum sensors technology, enable the future of computing. And maybe the thing to start with is I want to relate to the announcement that Johannes made in the beginning, and this countdown to the World's Quantum Day. I think one important message I want to give today is that quantum technology is not just in the future, but is really happening today. And that's one of the things, if there's one takeaway from my talk today, is really this. We develop solutions that are already used today by customers all around the world. To give you a bit of the context, I think it's not a surprise for nobody here that we're kind of expecting a tidal wave of data in the coming years. It started, it's affecting every industry sector, from medical to industry to manufacturing to our homes. And it's also not a surprise that this is starting to raise questions around how all of that is sustainable. It's estimated by 2030, the consumption related to this IC technology is going to represent 20% of the world's electricity usage. To put a number, this is the equivalent of 1,000 nuclear power plants. So just for these types of usage. And at the same time, as we increase the number of computers, sensors everywhere, you know, in data centers, but also on the edge, the question of how to manufacture them is starting to be more stringent. In particular, as we know that Moore's law is reaching an end, the cost of fab is growing every year. So we start to have some sort of important challenges here. Of course, and rather fortunately, there are solutions to that. And I wanted to highlight here two of them, which comes from this industry semiconductor roadmap. On the one hand, on the storage side, you have a technology called spintronics, which use the magnetic properties of electrons and materials to store information. Maybe the best example, if you're not familiar with spintronics, is a magnetic memory called MRAM. I'm sure all of you have heard of that maybe at least once. And the promise of that memory is really to be able to operate in a non-volatile way, but also in a much more energy saving fashion. The other side is related to processing, the computing power. And here, obviously, I wanted to highlight quantum computing and the promise of this huge processing power, but also at a lower energy footprint. So this is all very promising, but now if you really want to make the last step and move this technology from the lab and the final steps of product design to an industry, you still miss a number of components, and in particular, quality control tools, metrology tools to enable, to tailor the final steps of the product design, but also after that, to control quality in the production lines. The problem is that these materials, as I started to indicate, they rely on properties which are not standard. They are going a bit off the traditional silicon solutions. And in fact, a lot of magnetic properties become very central in these new technologies. So this is what I'm showing here. You have here a map on the left, which is showing different technologies, MFM, MOOC, SQUID, all of that are technologies to measure magnetic fields. And I'm showing how good they perform in terms of a resolution, lateral resolution, so how small the features they can see, but also how sensitive, which translate here in the thickness of the material that is needed to produce a certain signal. And as you can see, applications around MRAM, spintronics, or quantum computing is actually quite demanding for existing technology. And I'm not even talking here about the fact that, for example, in quantum computing, you need to operate in cryogenic environments. So here is the problem. We have a new demand and actually little tools to meet that demand. So the result is that R&D is still based largely on trial and error. People build designs and devices up to the end, they measure, they test it, and if it doesn't work, well, they try a new design, but with little information on what went wrong. And ultimately, that will also translate in production yields, which, for example, in MRAM are still pretty low at the moment. So the solution we propose is to use quantum technologies, quantum sensing technologies in particular, to measure these properties with unprecedented performance. And here is the QNAMI Proteus Q, so the core engine of today's QNAMI's business, and the first commercial quantum microscope that allows our users, we're talking here scientists and R&D researchers, to measure magnetic fields with a spatial resolution which will approach 10 nanometer in the coming years and is already 3 to 5 times higher than the competition, and an extremely high magnetic sensitivity. The main concept is to combine a technology which is called scanning probe microscopy, which is a microscopy technique for ultra high resolution with these quantum sensors that enable the extremely sensitive detection of signals. So if I come back to my map, this kind of puts us here on the top right in the perfect spot to try and support the development of these new technologies. So now if we look at how this is going to impact this business, I tried here to propose a map where on the bottom you have the error rate. So what is limiting this technology now, why it's still in the lab and not yet in production, is because error rates, whether it's for qubits or for MRAM bits, is still pretty large. And you want to control that so that you can go from niche markets, for example, showing or demonstrating quantum advantage. You need maybe 50 qubits and you can accept a certain error rate. But if you want to go all the way towards a universal quantum computer, you really need to massively improve on this error rate, the so-called quantum coherence. Going now into a bit more detail about the solution, it's not going to be a surprise here. We use the quantum system, and really what I want to say here, what I find beautiful with quantum sensors is that we particularly leverage what is typically considered a weakness of quantum system, which is their extremely high sensitivity to the environment. So if you're building a quantum computer, you're going to do everything to shield your qubit from the environment so that you can operate that qubit manipulate it in a safe environment and benefit from the quantum properties and superposition and entanglement and so on. When you want to do a sensor, actually this strong interaction, as long as you can control it, with the environment is a useful resource, actually a very powerful resource. So this is exactly at the core of what we develop. And more specifically, the technology we use is based on MV centers in diamond. Thank you, Matthew, for presenting the technology. I can be very brief here. But I want to say that why for us is this is the platform. It's not only because of the exceptional properties and performance of quantum sensors in diamond, but it's also because of the scalability. The fact that this is a solid state solution that you can think of engineering in the same way that silicon chips are made today makes this platform an intrinsically highly scalable platform. When I look at the NV Center, I see three main advantage that it provides to us. The first thing was highlighted by Matthew already. It's an atomic side defect. So it means it's the smallest sensor you can think of, and this impacts the maximum resolution we can achieve. It has this very complex quantum system and carries a spin. This spin is our quantum sensor, and this is the thing which is so sensitive to magnetic field. And lastly, the way it reacts to external fields such as the magnetic field is governed by fundamental constants. So when you have one NV center and you change for another NV center, the response is always going to be the same to the external field. So this leads to intrinsic repeatability, reproducibility, and accuracy in the measurement. This is key for us as we think of unfolding a technology for the industry. Going one step further, this is how we shape this diamond. In this particular case for scanning probe microscopy, the idea is to take a diamond that element 6 would provide, for example, and shape it into this purple form, which has a tiny needle. The idea of the needle is that we're able to bring the NV center, which would sit at the very end, at the apex of that needle, in the closest proximity to the sample. And then the rest of the design is made to optimize the optical collection, an important factor as was suggested by the previous question. So if we look a bit at what's happened to QNAMI in the past year, I think we start to observe traction in the market. We feel that the product we're building is meeting these expectations that I mentioned before. We already count 4 users in our customer base. We're extremely proud to have all of them. And I want to highlight 2 in particular. One is the research group of Albert Fert. He's the Nobel Prize winner and co-founder of the spintronics field as a whole. And the other one is the Fraunhofer Institute. Xavier is gonna talk just after me, so I'm really looking forward to see what's going on in the lab. But I think what this points out is that there is already an interest from the industry to understand the technology and apply the technology to solve their challenges. And this is exactly what the Fraunhofer Institute is setting up for, a test lab for their partners. And I could not resist just showing a couple of examples. I won't enter into the details of the physics at play here. I just wanted to highlight there's a broad range of applications. On the top left, you have a work done in the University of Dresden, where they fabricate this very specific memory cell based on completely new materials called antiferromagnetic materials. And NV magnetometry and our technology was really helpful for them to understand how these bits behave and finalize the design of their product. On the bottom right, You would have another example where the technology is applied in ultra low temperature environment. Well, low temperature, 4K. For some, this is not so cold, but for me, this is very cold. And here we show that we can map vortices in superconductors. This is a very key measurement for people working in quantum computers. Vortices can be a source of problems and a reason why the quantum coherence is not as high as they would like to. This is just a quick message in case in the audience there are people interested in this type of solutions, in this type of microscopy. They don't know if it would apply to them. We're also very happy within QNAMI in our own application lab to explore these applications, discuss your samples, discuss your research, discuss your products, and see whether or not we can help support the development of those research. And this is going to be one of my last slides. I just wanted to connect back to the beginning of the story. For QNAMI now, we're planning to develop and expand the capabilities of the Proteus Q that I've just shown, so that we can offer a solution that operates in cryogenic environment and be more specific in our value proposition to this quantum industry. And as well, we're looking to develop a solution compatible with 300 millimeter wafer. That is a requirement to perform meaningful support in the semiconductor industry. So this is what's ahead of us, ongoing developments. And of course, the home platform, the Proteus Q, is also being developed constantly for our existing users. So to conclude, I wanted to just say who we are. QNAMI is a pretty young startup still. We were founded in 2017. We're growing rapidly. We were 7 last year. We're 15 today. Still looking to recruit more. We're based in Switzerland, in Basel, at the crossroad between Switzerland, Germany, and France. But we also opened offices in Germany, in Freiburg, and more recently in Stuttgart, where we will kick some work in low temperature in particular. I want to highlight that our DNA is to collaborate, work with a lot of partners. I've mentioned Fraunhofer Element 6 already. Those are key partners for us to tackle scientific and technological challenges ahead of us. It's a long game, it's a long story, and it's great to have a very tight community around us to achieve these goals. And my last word is that we do have open position. So I invite you to spread the word, join QNAMI. It's a really fun team working on crazy challenges. And with this, I'd like to thank you for your attention.
Yeah, thank you very much, Mathieu. Yeah, I think it's really, really important to have deep insights into the applications of these technologies. And yeah, I really like what you are doing. So there is one question for you. What kind of positioning technology do you use for your quantum experiments, and how are the systems checked for resonance vibrations that distort the measurement signal or system? Even small vibrations can cause problems with the systems.
Yeah, so the positioning, so what we need in this type of microscopy is positioning with sub-nanometer precision. So we use so-called piezo positioners, which have this extremely high accuracy in closed loop most of the time, so that we can also come back to a certain position. Maybe the question is also how we're going to do that for a 300 millimeter wafer where movements are really large, and most of the existing technology struggle to offer this sub-nanometer resolution. I think this is work we're exploring right now, probably through a double deck of large positioning and very fine, accurate positioning, sub-nanometer positioning on top. And for the vibration, I mean, we have I don't know the details, but I could certainly connect that person to our engineers. But there are very standard tests for measuring vibrations. Ultimately, the quality of the image and the quality of the data we take is the one that speaks. And of course, these systems benefit from a quiet environment. They are offered in a shielding environment if necessary. But I have to say that for most research environment, let's say medium to high quality research environment, not much is needed in this regard. The platform is extremely stable. I don't hear you. Maybe you're muted.
Oh, sorry. Yeah, I just said that I will make the connection to the guy who asked the question. And one other point from the question was that the systems maybe should operate at millikelvin temperatures, but this is for diamond sensing not the case. I think so.
It's a good question, because if you want to really support the quantum computing industry, you want to know at what temperature you can measure something which is meaningful to them, and ideally you would think we should be at the same temperature where these systems operate. That's true, but the price you have to pay is cool down time. So there is really a trade-off to study here between a measurement which is exactly mimicking the environment and a measurement which can be faster and a sample turnaround time that can be much improved.
Okay, yeah, thank you very much for this great talk and your answers. So then we can directly go to the next speaker. And as Mathieu said, he's also very happy to hear more about what's happening in the lab. So I'm too. And yeah, I'm very happy to welcome Xavier Vidal. He's research scientist at Fraunhofer IAF, the Institute for Solid State Physics in Freiburg. And his talk is about an approach to quantum sensing at Fraunhofer IAF.
Thank you for the introduction, and thank you for inviting me. So yes, in the following minutes, I'm going to present the efforts that we are doing at the Fraunhofer Institute for the Applied Solid State Physics on quantum sensing, and particularly on quantum magnetometry with MV centers. An introduction to the institute. So Fraunhofer IAF in short, and has a long-standing experience and knowledge in 3-5 semiconductors and diamond technologies. The institute, electronic and optoelectronic devices, as well as integrated circuits, are developed, and also as well as semiconductor lasers. And from the diamond technologies, some efforts started to put together, creating a new department on quantum technologies where I belong to. And the institute has also been participating for several years already in national and international projects on sensing using this the diamond technology. And I would like to highlight QMAC. It's a project that tries to measure quantum magnetic fields using MV centers and also OPM, but the efforts at the institute, which is the institute leading this project, is on MV centers. And this project was acquired 2 years ago. That's the moment that I arrived to the institute. And I'd like to highlight this one because it has all the points that we need for quantum sensing with MV centers, from the fabrication all the way down to the application. I'm going also to skip this slide, so I'm going to use the words from Matthew that he already explained, the mechanism of the MV centers, just to insist that for the measurements, what we do is we scan a microwave frequency, and then we see a reduction of the emission, and then we know which is the state. Then we have these two dips on the Zeeman splitting that in the energy levels, it's represented here, okay? And then that distance is proportional to the magnetic field, okay? And I want to highlight this because this is going to be the essence of many of the measurements that we do. Another important property of the MV centers is that it has a long coherence time, okay? But for that, we need a high quality diamond that hosts the MV center. So that's why we also grow our own diamond. For that, we do this chemical vapor deposition on commercially available diamond substrates. This is one of the image of one of our reactors. And here we can control different factors that will keep this long coherence time of these MV centers. We can, as has been also mentioned here, we can control the strain, and that can affect the coherence time. We can also improve the morphology. For instance, here you have an image where the surface morphology has been improved from macrometers to just few nanometers only with the growth. Then also to have this coherence time, it's important to reduce all spin noise, all magnetic noise that is naturally on diamond. For instance, color centers that are naturally there but that are unwanted, like nitrogen vacancy centers itself, or silicon vacancies as well. This is, for instance, one of the processes where you can see there is no signal at all, only the first and second Raman peak. That is also an indication of the quality of the diamond that we grow. With this effort of removing spins, we also can control the carbon-13 and carbon-12, this ratio, because carbon-13 has a spin that is not zero, and then can be also a source of noise. And then we use this for this fact also to measure which is the thickness of the layers that we can generate, and also how sharp are those layers. And here you see two examples by secondary mass spectroscopy, where on the left it's a substrate where the crystal axis 100 is perpendicular to the surface, and on the right is the 111. In the first one, we can get thicknesses of down to 20 nanometers, and for the 111 to 70 nanometers. So yes, the results depend also on the substrate that we are using. So up to now, what we have here is pure diamond, and then by nitrogen irradiation that we do externally, we create those MV centers. But we can also grow the diamond doped with nitrogen, where again we can control the isotope, and that will be important to measure how much nitrogen is incorporated in those layers. And then to this process, then with the way to generate these MV centers by electron irradiation. There is a third alternative, which is the one that I'm particularly interested, is when the MVs are formed during the growth. And in particularly when we have these substrates 111, okay? Because on that case, controlling the parameters in the reactor, we can generate the MV centers all in the same direction. So in a natural situation, you have a monocrystal lattice, the MV centers are in 4 directions due to the crystal of the diamond. So here we are able to generate only one direction, all perpendicular to the surface. So this is an example of one of those samples that is the sample that I'm going to use for the following slide. So it is just to be a little bit consistent with the measurements. So here you have an optical image, and then you see the emission is just pure NV minus. We try to characterize optically that sample, what's the thickness of that layer, but it's much below the optical resolution. That's really what we were looking for. So we believe it's around 300 nanometers, considering the time that the nitrogen was in the reactor. And then to prove that we have only one direction, we apply this technique that I mentioned before, this ODMR, where we put a magnet in different directions, and we have only one Zeeman splitting. Okay, that's what you can see here. Instead of the 4 directions, that will be schematic schemes here, that will be something like this. Okay. And so this is about what we can do on characterization using continuous laser microwave, but we can also characterize our samples or using these relaxation time properties. So for that, we pulse the laser, the microwave, and detection synchronously with different sequences. These schemes are here. I'm not going to detail on that. But then we can extract T1. For instance, in this sample was quite long, more than 5 milliseconds. We can measure T2 star by pulse ODMR. And in this sample is 1.67 microseconds. And I have to say here that we are at the theoretical limit of T2 star with with respect to the concentration of nitrogen, okay, of P1 centers. And also we can measure T2, okay, using other protocols, although this is from another sample. So what are the platforms that we have at the Institute? We have the laser threshold magnetometer. This is the first application that we had at the Institute. This is a project led by Jan Jeske, where the idea here is you have a diamond with a high concentration of MV centers. You put it in a cavity, it will lace, and then from that lacing and the threshold, you have a high sensitivity. As I show, we have this confocal system for MV magnetometry that we can use also for sensing, for measurements. Now we are building a wide field magnetometer. That the great advantage is that instead of scanning, you have a full map of the magnetic field in a single shot. You will lose resolution, but if you want, for instance, to look at a dynamic system, that will be relevant. And we have acquired 3 MV scanners, I would say that 3 that are on the market. And all this together is put it in this application lab that already Mathieu mentioned, that we are trying to also to attract the partners and researchers and companies to test our samples with us. So about the applications, I can mention that we are working on nanoelectronic circuits or microelectronic circuits to try to measure the magnetic field, also different materials, but I'm going to focus on our latest results on magnetic nanoparticles, because it will touch several of those applications and platforms. So we have these magnetic nanoparticles from Fraunhofer IMM, again in this consortium of this QMAP project. And the first question was if we were able at all to measure the magnetization of those particles. So we put those particles on top of that diamond layer that has been shown until now. And you have here an optical image where you see small particles, and here the concentration starts to increase, and here we have this big cluster, okay, of particles due to the evaporation creates this ring. And on the right, you see the PL emission from the MV center that are underneath. This black region here corresponds to this cluster of particles that really they are just blocking the light. Okay, but to be sure that we don't have any artifact, we measure the spectrum at different points. For instance, in these 4 points, you can see the spectrum, again, is just pure NV minus, just the intensity changes. So then the idea is we scan in different directions. At each step, we measure this optical detector magnetic resonance, and then from here, we extract the magnetic field. So we have a bias field, which is this indicated here with this red light, and then yes, we are able to measure the magnetic field. This is this blue line. To be sure, again, as a control, that there is no correlation with photoluminescence, because the measurement depends on the contrast, not on the intensity, although the intensity helps to improve the sensitivity. We see that there is no correlation only in the black region, okay, which is what you see between these 2 black lines. And that's expected, no? So we have less light because the light is blocked by the particles. Huge amount of particles increase the magnetization, the magnetic field. And this is other measurements in the other direction, just to prove that this is solid and everything makes sense. So the following question was, okay, can we measure small particles? And for that, we then used our MV scan magnetometer from QNAMI, the Proteus Q. Okay, we put particles on top of a silicon wafer, and then the first try we're trying to measure the magnetic field of few particles, even trying to see single particles. So, and that's what you can see here on the top. There are 3 particles, and here very we can see the magnetic field. This is an image which is not treated. Okay, this is as it is, and now you can make it better and nicer. But I wanted to show this raw data. We are still mastering the system. I mean, it just arrived not even half a year ago, and well, it's hard to be in the lab in those days. But then we measure a bigger amount of particles, still a small cluster, and then the signal was much more clear. You can see the particles here and here, those clusters, and the magnetic field is very clear. We have a change of 3 millitesla. So next step was to measure even a bigger cluster. And this is what really we were expecting, that we were not able to do the measurement. And the reason is because it's been in contact with this big cluster, the electron of this NV minus, okay, because just to remind what he has explained, this is a diamond probe with a single NV on the tip. The NV minus was attracted by the magnetic nanoparticles with this big cluster and then gets ionized, or because there is a strong magnetic field perpendicular to the NV center that does not allow to initialize the system. So we have what is called this spin mixing. So we don't have ODMR signal. Then, trying to find what was the answer of these two options, we then scan at different heights, so we are not in contact anymore, and then we recover the signal when we were at 475 nanometers. That's important to say that this is still the same tip, okay? You don't need to change the tip, just that the signal, it's recovered. Okay, so then, I don't know to say if this was a lucky or unlucky situation. We got particles attached to the diamond, so you can recognize the diamond probe from Q9 here, and you see particles attached to the tip. So we were wondering, okay, so let's see if we can really figure it out if this is the transverse magnetic field or just this attract by the sample, no? So then what we did is we know the crystal orientation of the diamond, so then we try to magnetize those particles in the 4 possible directions where we expect to have the single NV. And then that was quite clear. We were able to see that the magnetization was in the plane of the particles. I forgot to mention that those particles are 40 nanometers length, so the longest length is 40 nanometers. They are like hexagons, and they are only 5 nanometers thick. And we see that they are all, that's what we deduced from our measurement, they were all on the plane, which is what also we expect from literature. And then my final result here is that now then we were also wondering if we can use those particles for sensing. And then we put those particles on top of the diamond plate, the same as has been shown before. And you can see that there is a strong reduction of T1. We start with T1 because it's the easiest to measure, and we also expect the biggest change. And in fact, we have 1 order of magnitude change. And from here, we will do other kind of characterization, but the point is that then we can go to applications on microfluidic chambers or even in biology system, which is something that people is already doing. And also we want to see if we can control the distance between the NV layer and the particles to also manipulate the coherence properties of the NV center, how they change with the proximity of this induced noise in magnetic noise in some way. So as a summary, here I would like to mention that we can overgrowth our own diamond, so we can control the spin. We can also grow with direct formation of NV centers, which is the results that I show here with this 111. We have all tools for doing the characterization and improving them. We have different platforms for NV magnetometry, and I would like to add to that list a fiber magnetometer that we are also working on, and also equivalently, instead of measuring the magnetic field, we can use the same technique for measuring microwave sources. Applications, material science, as you already see. So there are other materials also that are under investigation. The magnetic field generated in micro and nanoelectronic circuits, as well nuclear magnetic resonance with NV centers, a project that is coming now, and open to all your suggestions and collaborations, and that's why we have this application lab in synergy with the QMAC project. Thank you for your attention, and I would also like to thank Aaron Ensling, who is the person who is behind all those measurements on the magnetic nanoparticles.
Yeah, thank you very much, Xavier. It's really impressive what you're doing there in Freiburg. There's one question for you. Sorry. Is it possible to use NV centers for brain sensing? Are they sensitive enough? Can you measure a range of nanotesla, for example, to build brain-computer interfaces?
Yes, that's one of that's possible. This is one of the aim of those what I was saying. This optical fiber magnetometer. That can be the aim. The sensitivity can go down to picotesla or even below with this laser threshold magnetometer. So yeah, that's possible. The point is how to reach the position of the measurement because that could be on the surface of the brain. But yeah, I mean, it's possible.
Okay, great. Yeah, then thanks again for your talk. And I have one quick question to all the speakers. So what are your recommendations to other startups, organizations in general, or Europe in general, on how to achieve European industrial leadership in quantum? So yeah, maybe you can share your thoughts on this, and maybe you have a recommendation. So Frank, would you like to start?
Well, I mean, I think it's, I mean, I'm mostly a scientist, so it's maybe I'm not the greatest authority in this. I think it's keep being open to all possibilities within Europe. Yeah, I think it can be achieved by having a lot of collaborations and looking in all directions, and also accepting like help from others and seeking help from others in solving the challenges. I think we pretty much all know the challenges, and many of us have an idea of what to use quantum technologies for, and now it's about solving them together.
Yeah, thank you very much. Markus, do you also have some thoughts on this?
Yeah, I mean, pretty much agree. It's now at the edge of not only implementing, but fastly implementing. So accelerating from all sides. I think it's what you see, and you know, from all the funding and support initiatives. I mean, thinking as a researcher at university research institute level, and as a company, I mean, there's a good, I think, network of funding opportunities drawn now. I mean, the only thing which always is a little bit to discuss is that if you want to really, you know, make a big step in technology development for specific key aspects. I mean, there are many. They're similar in all aspects, or you know, applicable to many aspects of quantum sensing. That I think one needs to really acknowledge that there is still a lot to be done, and this is very. I mean, it's not very, you know, easy and funding wise something you can do just in parallel due to some system verification. You really need to have very, I would say in German translated, dry technology programs, which maybe are not addressing in the end, I implement something in a demonstrator and show that it works, because that is something which, you know, we have been doing the last 10 years and that works. We really need to focus only on specific steps of technology. And that means it's longer projects. They are a lot of resource intense. And yeah, they should just, you know, path the way that we then can all put the applications really into let's say a level of swap you can use in the outside world. So a little bit more courage towards very dry technology programs. That's maybe one of the things I just want to add to the discussion.
Yeah, I totally agree with you. Okay, thank you very much, Markus. Matthew, what are your thoughts on this?
So I think I can sum it up in effectively one word or two, a few words. Innovation has no boundaries, I think, and my concern for the Horizon Europe program, which I've been involved in European projects since 2007, and if UK isn't allowed into it, which is looking very likely, I think it's not just sad for us in terms of ability to help drive this technology forward through collaboration. It's also it's basically a lose-lose scenario, I think, for Europe and the UK, which will be a real shame if that happens. I mean, hopefully we will find processes where we can work together with both the academic groups. I mean, we obviously will still work with the industrial partners where we can, but I think that's what we really need to do. I think to get these technology, out there in the markets and really progressing, we need this collaboration, we need this network, and innovation doesn't have borders. That's my summary.
It's a great thought. Yeah, innovation doesn't have borders. Okay, Mathieu, any thoughts on this?
Yeah, I was thinking of three main points, and the first one is the same. I mean, if we want a European ecosystem, let's think Europe as a continent and not exclude UK, for example. It's just such a bad mistake. So this is more a message to our politics and authorities that, in Europe, but also in individual governments, there are some decisions which just don't make sense. So yeah, this is very important. More for the startups, I think I would give two advice. One is it's a long way. It's often starting with pretty low TRL. So I think connecting with academics is really essential. We do see a desire and from these partners to work with industry more and more. I think the relation starts to really function. It was maybe not the case decades ago when I started my research. There was little interface between industry and science. I think this is growing and this is starts to functioning really well. So I would advise companies, young startups, to try and also engage into these relations. And the second one, or the third point, is really to contribute to the development of the talent pool. There is still, a shortage of quantum engineers and people with the ad hoc competence. So it's really everyone's responsibility to go out, talk, give to the young people an interest into the technology, give them the sense that there's something great happening there, and they should consider that in their career path. And so yeah, I think this is for everyone to do, so that we can all benefit. It's not like you individual are going to go out, make a convincing case to person A and get that person A here. You will convince person A, and person A will work for a company, another company, and this other company will convince another one that will work with you. This is how it will work.
Yeah, very important things, I think. Yeah, thank you very much, Xavier. Do you also have some recommendations?
It's hard to me because I'm also a scientist, but yeah, in that case, I would like to address my message to the companies. They have to, these big companies, they have a lot of resources, but they are not brave enough sometimes to really go to the quantum technologies and support our research. And this is a benefit for everyone, obviously for us, but mainly for them in the long term. And that's what they have to be looking at, and not just leave all this effort to small new spin-off startups like Qnami, for instance. No, they have also to bet on what we are doing, because that's the future. That's clear.
Okay, yeah, thank you very much for all your recommendations, and I hope we can work together on this. So it's also a mission of QBN to avoid small kingdoms, as I always said. So I try to work on this more harder. So yeah, thank you very much for all your brilliant talks. And I think we saw that yeah, there are impressive improvements of the senses of our digital life, means the quantum sensors and imaging devices, and that quantum technologies are able to enable these developments. And yeah, thanks again to the speakers and to all the participants. And yeah, don't forget to subscribe to our YouTube channel for further European quantum leadership sessions and QBN webinars, and give us a thumbs up. Make sure you follow us on LinkedIn and Twitter, and yeah, see you in the next European quantum leadership session or QBN meeting. Stay safe. Thank you again, and bye-bye.
Thank you.
Bye.
Thanks.
Bye.
Thanks a lot.